Hello, I'd like to introduce to you RadPuff. RadPuff is a radiation dispersion projection software developed by microsimulation technology. Uh, it is used to predict radiation dispersion device, RDD. A common name is 30 bound. The radiation source released to the atmosphere. How much is the downstream dose rate and integrated dose projected using the real-time meteorological condition, wind direction, and wind speed. So the authority could advise the people in the plume whether they should evacuate or use some kind of protection defense. And the source could be either RDD, that's a isolated source with its spectrum cover every possible nuclear isotopes. We have 52 of them. And in this table is alphabetical order. Started with American 241, and that's artificial one, a fission product of a nuclear power plant. And such as cesium-137, that's a very long lifetime cesium gas, and that could be harmful for hundreds of years. And you may prepare the source, or you may use, if the source is some fission product release from the nuclear power plant, then we can use the plant release, and that is connected to our another product called PCTRAN, that either a normal operation or a severe accident such as Fukushima, the time release projection is saved into access data file. So suppose we now use the RDD default source term, and which is cesium-137 for 1,000 curies. It's pretty large, source. And close the table and click OK now. And the default map is where the release will be from the center. And suppose you use this in the field, and we choose a new map, and the address by either longitude or latitude or by the street address. We use Google Maps. Suppose we use the city of New York. I type in New York. Of course, you can type in the exact location. And here, simply choose by address. All right, Google Map will give you New York here. And let me eliminate the commercial part of Google and put New York into the center of the map. And since we want to know close range and from scale, this is 2 miles. All right, so from the left to right or top to bottom, we have a square map. It's about 10 miles. So I put in 10 miles for the range and submit map. And now you see the background is New York with a 10-mile range or 5-mile radius map. And now the meteorological condition, the wind velocity, suppose for that day is 3 meters per second. And wind direction, suppose is from southeast to northwest. And convention is 0 degrees pointing to the south. So from here to here is about 120 degrees. I put in here. And those conditions you can get from internet. Any weather service would tell you. And the release height, suppose it's from 20 meters above the ground, 7th floor building. And the temperature of the ground and the 1 meter height is useful because that determines the Pascal stability class A to F. So, we don't suppose the ground is 50 degrees and the 55 is the above ground. So the software determines which Pascal condition class of dispersion. And the release time is 1,000 seconds. That's so you can put in any number for the judgment. And click OK. And this icon start to run. Here now the atom with 2 electrons spinning means the software start running. And it's a real time, 1-to-1. Since we want to do the projection, so I can speed it up to 2, 4, 8 or up to 16 times. Let me use the maximum speed. You see, here's the radiation source. So instantly, the heavily contaminated area actually happens to be in Brooklyn. Okay, the Gaussian puff model is used in solving the differential equation, and the plume is color coordinated. And right now we are calculating the TEDI. That's a total committed dose of the whole body in the units of suppose I click anywhere in the plume. Digitally it will show the TEDI dose rate in rams per hour. The ram is pretty large unit. 1 ram is normally we use the dosimeter use milliram. Okay, so those are the heavily contaminated area, and the authority may give some advice to people in the area. Suppose the wind direction change. So far we already run almost 900 seconds. So that's about 15 minutes. We accelerate doing projection. Suppose this time you read the weather condition from the internet, the wind direction change to 150 degrees. We click OK, and you'll see the plume shift to further north. Okay, it's dispersing into the New Jersey area. And we can keep doing that. Suppose it turns to 180 degrees. Click OK. It will project. You see the front of the plume reach New Jersey. So this device gives you a projection capability according to your source term estimate to have a downstream projection. See, if I click here, the dose, it will be nothing, right? The natural background that would not have counted in the software. And other than TEDI integrated dose, we can have Oh, this is dose rate, sorry. We can have the integrate dose that's at certain location. We can also have the integrate the thyroid dose because thyroid mostly affected by noble gas iodine release, and the thyroid dose rate. So this software gives you a method to project two-dimensionally dose distribution anywhere in the world. It's a 2D model. Well, we do consider the release height. Different height affect how much dispersion. Doesn't account for terrain, hills, buildings, and all those local physical terrain. Hope you get some idea, and thanks for attention.